Hi, and welcome to this next clip in the acid and base series for A-level chemistry. In this one, we're going to look at a slightly different topic in that we're going to look at a practice calculation that may turn up in an exam, in that we have been used to now looking at the concentrations of strong acids we'll look at in this example. So we're aware of the situation whereby if we had a hydrochloric acid solution of 0.15 moles per litre, we can very easily evaluate the pH of that now by putting that into the minus log to the base 10 equation, which we've seen a few times now. And if we know that HCl is a strong acid and completely dissociates, then the H plus concentration will be 0.15. And if we were to evaluate that calculation, we would have a pH of 0.83. And we've done that in a previous clip. What we're now going to do, though, is take a situation which may happen during a reaction where if we were to take 25 centimeters cubed of it, so say it was a titration, and we were to react that with, for example, sodium hydroxide, then we know through acid plus alkali chemistry that that would produce sodium chloride plus water as a product, and so the HCl would undergo neutralization with the strong base in this situation, which means the concentration of H plus ions would subsequently decrease during that reaction, and as a result the H plus ion concentration would therefore change, and subsequently the pH would change. Now we know from general knowledge that that would probably relate to an increase in the pH, but using calculation we can actually work out what that change would be. So if we were to assume that we had a 0.2 molar solution, obviously within an exam situation these numbers would vary, but if we were to say we had 5 centimeters cubed of that 0.2 molar solution added to it, then a question may go along the lines of what is the pH of the resultant solution? And so what we would need to do in this situation is initially calculate the number of moles of each of the substances, and we'd do that by using the MV over 1,000 equation in both examples. This would allow us to calculate the number of moles of the HCl by taking 0.15, multiplying by 25 and dividing by 1,000. That would give us a number of moles of 0.00375, and that would be the number of moles of HCl that we started with. If we were to do the same thing for the sodium hydroxide, and we were to take 0.2 multiplied by the 5 and divide by 1,000, that would then give us 0.001 moles of sodium hydroxide. And we can see from there that what we have is a situation whereby the moles of HCl are larger than the moles of sodium hydroxide. Now, if we assume that complete reaction will occur, then the excess of HCl remaining is going to equal the 0.00375, subtract the 0.001, and that will leave us with 0.00275. So that will be the number of moles of HCl remaining. We're then going to need to calculate the pH. Now obviously, in order to calculate the pH, what we would need is to reevaluate what the concentration of the H plus is going to be. And so by a rearrangement of this equation over here, whereby we want to try and calculate what M is, or C if you use CV over 1,000, then the concentration is equal to the number of moles I now have multiplied by 1,000 divided by the volume. So we already have the number of moles of the excess HCl now, which is 0.00275. we would need to multiply by 1,000. The 1,000 is used to convert volumes in centimetres cubed into litres. And the volume is now equal to the total volume of the solution. Now remember, we had 25 centimetres cubed to start with of acid, but we've now got this additional 5 centimetres cubed. So the volume is now in a total of 30 centimetres cubed. This, when we evaluate this equation, now gives us a concentration of 0.917. Now that is obviously, we can compare that value with the initial one, and we're happy to see that that concentration has decreased, which makes sense because we've reacted some of the HCl out of the solution, and also we've diluted it by increasing the total volume. So both of those factors lead to a decrease in the concentration value, which now means that if we introduce this into our minus log base 10, again, assuming that HCl is a strong acid and completely dissociates its H plus ions, this will then lead us to a pH of 1.04, rounded to 2 decimal places. Depending on how you've rounded some of your previous answers, you may get a slightly different figure to the second decimal place there, but as long as you followed that methodology, you should be in the region of 1.04. Remember, we would usually give pHs to 2 decimal places in these types of calculation. You could obviously therefore use this if a question had changed the numbers by using different volumes or different concentrations. Likewise, it would work. You may just have to do slightly different balancing of the equation should you be given a diprotic acid or a dibasic base, for example. But hopefully that gives you a bit of an idea how we could then calculate the pH of a strong acid after it's done a reaction with a small amount of base. In the next clip, we'll look at some weak acid interactions, which again will follow the same thing, but we have to introduce the Ka again into that equation, and then we'll move on to the final variation of the calculations, whereby we look at the pH of buffers as well. So thank you for this one, and I will see you in the next one.